please.
Okay, great. So now we've heard a lot about new display technologies, and I want to recap a little bit, but also then talk about the measurement challenges you have with some of those technologies. So here's a quick overview of developments of the last years. So we still use, to a large extent, TFT LCDs. OLED, AMOLED displays are very common now in our smartphones. And since 2013, we had the first introduction of QLED, that means with the quantum dot technology. MicroLED was introduced in 2012 already, but the first real product 2019, and that is something which is now, like we heard today, really strongly evolving. And for different areas, we have since 2022 quantum OLED, and are now looking into so-called true QD LEDs. That means self-emissive displays in that case. And those new display technologies provide some advantages, especially that they have a very high dynamic range, very low luminance values, very high luminance on the other side they can achieve. And that can be a problem, or at least something you have to take care of when you need to measure that. And when we are talking about low luminance values, we are talking typically about 0.01 candela per square meter, or typical real world very low values are 0.005 candela per square meter. Can be even lower than that, because OLED, for example, by definition, does not show any light when you switch off the display. So you have infinite contrast in theory. Of course, then in the real world application, you have some reflection on the display. But from the low luminance value, you can go very, very low. On the other side, the new technologies, like we just heard as well, can go up very, very high. So it's now very common that you have displays with 3,000 candela per square meter or 5,000 candela per square meter for outside applications, or when you have small displays and you have to realize really high luminance values as well. You have displays with 20,000 nits and above, even for backlight units, really high values up to 100,000, which you need to measure very accurately as well. Then the new displays have one advantage compared to our old CRT-based Rec 709 color gamut. They achieve a very wide color gamut, which is now, for example, defined in Rec 2020. And to realize this large color gamut, you need to have a display where you have the typically 3, but can be any other number as well, not any, but 3 or more primary values. They need to have a very narrow spectral power distribution. And then you can achieve a really so-called wide gamut display with very, very saturated colors. But that can be challenging to measure as well. For AR/VR applications, but also for applications like, for example, a smartphone, you have very small displays you need to measure now. In some cases, you want to evaluate on a pixel level. And finally, you also need to take care that you assess the viewing angle characteristics of your devices. Most of the modern display technologies have a pretty good and very not so strong dependence on the viewing angle. But to achieve that, especially in the development phase, it's important also to characterize the viewing angles. And some technologies still have some problems with that as well. And what do we measure? So first is the brightness. Brightness is not the correct description of that. The correct name is the luminance, which we measure in candela per square meter. But the luminance directly correlates to the brightness we perceive as a human. The next value we typically will measure is the so-called chromaticity, mostly expressed as small xy values, but you can also transfer that to other color coordinates. They are calculated from the pre-stimulus values xyz. and then describe a specific color. And you measure, for example, red, green, blue, white, and black, several gray steps typically, but for some applications you might measure, for example, even up to 5,000 color patches, for example, to calibrate a display, a TV. That is an application where they use a really large set of colors. And that means you also need to be able to measure very fast to make all those measurements in a reasonable time. And then finally, in some applications, you want to assess the spectral power distribution as such. So here is an example of a SPD from a quantum dot enhanced film. And you see that it's also relatively narrow, but can be even narrower than that. That is a relatively old picture. And there are two possibilities how you can measure all those values, so the luminance, tristimulus values, or the spectrum. You can either measure a single spot on a display, so that can be a very small spot, 1 or 2 millimeters only, or it can be a larger spot. Typically for not too small displays, you will measure a spot size of a few centimeters. So you want to assure that you have at least 500 pixels at the same time in this measurement spot, so that you are not dependent on slight variations in the placement of the probe. And then the second possibility is that you want to assess the color characteristics and everything spatially resolved with a so-called 2D imaging colorimeter. And Admesy offers for both of those measurement types, spot and 2D imaging measurements, different solutions. Our Prometheus series for spot measurements and the Titan and Helios series for 2D imaging. So when we have a look at the luminance range we want to measure, the first thing we need to take care of is the low sensitivity, or sorry, the low luminance range. And to measure very accurate, you want to have a very high sensitivity. So with our colorimeters, we can measure down to, and now you have to count, 0.0000025 candela per square meter, so extremely low luminance values in just a second, or more typical would be 0.005 candela per square meter in half a second with a really good signal-to-noise ratio. You also need to make sure that you have a good handling of the noise characteristics, so dark current calculation. For some devices, you use a cool sensor, and for our spectroradiometers, for example, we achieve a super large dynamic range of 0.005 candela per square meter up to 10 million, and have an excellent signal-to-noise ratio of 1300 to 1. The device uses neutral density filters, which also helps to achieve that large luminance range. And for the colorimeters, we have a ultra-high luminance sampling mode, which extends the luminance range even further, also for the colorimeters as well. To measure the narrow spectral peaks, you need to differentiate between the colorimeter or spectroradiometer type of instruments. So when you're looking at the colorimeter type, then you want to have a small F1 error. That means those curves you see here, those are the so-called color matching functions, and they describe the vision of our human eye, so the sensitivity of our eye. It's not the sensitivity of our cones, but it's correlated to that and basically comes down to the sensitivity of the eye, how we perceive the colors. And so you need to make sure that the filters you use in those instruments are very accurate and that they match to those target functions as good as possible. And a small F1 error of, for example, about 2%, which is exceptionally good. That means to compare the area you have under each curve from the target to what you achieve has a mismatch of, for example, 2% is exceptionally good. And then you have a very low uncertainty of the color value you will measure. And the same is true when you look at imaging colorimeters. In an imaging colorimeter, you have the additional neat that you also need to make sure that the filters are not only accurate as such, but also over a very relatively large area. That is a bit harder to achieve even. For the spectroradiometers, you need to make sure that you measure with a high resolution so that you can resolve all those small spectral bandwidth peaks. We offer instruments with an FHWM, full width half maximum resolution of 2.8 nanometers or smaller, but that can be customized with different slit sizes or gratings of the instrument to really match the target of a customer. And the wavelength accuracy of such a high-end spectroradiometer is really, as good as it gets, what you can physically achieve with a wavelength accuracy of only 0.06 nanometers, so extremely accurate. You can describe those small peaks. And for small displays, you of course need to make sure that you have small probes, so with a small measurement spot, and that goes down typically for our instruments to 2 millimeter. And for the spectroradiometer, you have even the possibility with a small measurement angle you can choose in the instrument and a macro lens to go down to 1/3 of a millimeter as a single measurement spot. And finally, we will have a look at the viewing angle characteristics. So for that, it is important again, for a colorimeter, for example, you can realize that with different acceptance angles, that means the angle under which the instrument collects the light from the display, and you want typically to have an acceptance angle of 5 degrees or less, because then you will not take into account the light rays which come from a very steep angle on the display. Because if you would measure with a wider acceptance angle, you gain sensitivity. That is the advantage. But the disadvantage is that you average or you smear out the measurement and do not really describe the display from the perpendicular viewing direction, but also take into account light rays which come from an angle which are typically you don't want to measure in that case to make a spot measurement. And this is a difference we compared to our competitors, that sometimes they use a larger acceptance angle to get a higher sensitivity, but with our patent pending electronics design, we can achieve a super sensitive device and can then use a relatively small acceptance angle to have very accurate color measurements. And then for some instruments, it's also important that you have a low sensitivity to polarization so that you don't get errors depending on the polarization direction of the light. And in the end, when you want to assess the viewing angle, so exactly describe under which angle a specific color is seen, then you can do that with a so-called cornerscope, which measures a single spot, but this single spot collects the light from all the different angles, for example, plus minus 50 degrees, and then tells you in a resolution of, for example, 5 degrees, the different colors you will see under different angles. And that is a measurement which can be done with one measurement shot, so to say. So as Admesy, we offer time-proven, tested display testing solutions. So we are now in the market since 2006. And the solutions are very accurate, easy to integrate in production environments, and very robust. But we also develop custom products, and actually many of our standard products started as a custom product that a customer said, I have a specific need, and can you develop something for that? So we have very innovative designs, some patents pending, especially our experience in high-end filter coatings is now very interesting. This is something where we are always looking to find partners, not for the filter coating, but in general, in all areas when you think it could be interesting to work with us together as a potential partner, or if you have ideas for a product, if you have measurement needs which are not covered yet good enough with the current equipment, just reach out to us, and then we can see what we can develop together.